Hi everyone, welcome. We are presenting simple LM-powered CLI, a terminal-first AI assistant. So here is the roadmap for this video. Kickoff, why and what, architecture, key features, report and demo, and wrap up. Let's start with part 1, kickoff. In one line, this is a Rust TUI and CLI assistant with a tool using agent. My circle chart history, and streaming from a local OpenAI compatible endpoint. Our team member info is listed on this slide. Next is part 2, why and what. Why we built it and what problem it solves. The motivation is quite simple. Many AI chat clients are very heavy and not scriptable and not local first. So we want something that lives in the terminal and feels fast. So we built a lightweight assistant that can act, not just chat. And we use Rust for performance, safety, and strong async I/O, which matters for streaming output and DB access. Our core objectives are four pieces: dual interfaces, TUI plus CLI, local streaming, MyCircle persistence, and an agent loop that runs plan to execute to verify before it answers.
At a high level, the front end are source terminal UI and source CLI. The agent core is source agent planner, executor, and verifier. Tools lives in source tools registry, persistence is handled in source database, and the LLM client is in source WebSocket. There's also an optional local HTTP server in source MCP servers to expose tools through tools evoke. Next, explore for key features. Feature 1 is Red Hat's UI TUI, a full terminal chat experience that stays inside the shell but still feels like a real app. You can see the conversation list, messages, and most importantly, panels for plan, execution, and tools results. Controls are optimized for speed. Enter to send, Control plus N to new, and Control plus D to delete. Arrows to navigate, and page up and down to scroll, and Q to quit. Feature 2 is CLI, which supports both interactive and scriptable use. For a repo session, cargo run --CLI and :Q to exit. For automation or quick task, run cargo run --S once, and it prints the full pipeline so you can literally see plan, execute, answer in the terminal. Feature 3 is agentic workflow. The first is plan. The model proposes JSON steps with tools and parameters. The second is execute. We run steps in order respect depends on and can autofill missing parameters from the prompt. The third is verify. We check whether each step succeeded and only then feed the result back into the model context for the final response. The example here shows a web fetch plan, execution storing result, and verification injecting context. Feature 4 is tooling layer. We have tools for file system operations like ls, cat, write, make directory, remove, execution tools like shell and git, HTTP via web fetch, database queries like list conversation and get messages, plus editor style helper and optional ACP and ANSP integration. One important honesty note, the denying list is tool name only and shell is not sandbox, so user responsibility matters. Feature 5 is persistence. Every chat is saved to MySQL, so you can restart the app and continue where you left off. Tables are auto-created for conversations and messages, and the terminal UI gives you scrollable history. There is also an optional seeding using seed sample data for quick testing.
Hi, I'm Peixuan. Now we are moving into part 5, repro and demo. The goal here is to show that this project is not just a demo on our machines. You can reproduce it quickly, and the demo flow will behave the same way. To make grading and testing straightforward, we summarize the reproducibility into 4 steps. First, you need to set the LLM base URL link and LLM model to point to your local AI server, for example, LM Studio. Second, you need to configure the database userlink and create the MySQL user and database. Third, you need to run the cargo test to verify the setup. Finally, you need to launch the TOI with cargo run. In practice, we recommend doing that one-off check first because it quickly confirms the LLM endpoint is reachable. Our client does a simple health or model availability check, and then you can move to the TOI with confidence. Here is a demo of the TOI. You can see a new conversation here. It asks the assistant to read the content of a file, and you can see the full agent pipeline inside the terminal UI. First it plans, then it executes, and finally it streams the answer token by token. We'll point to two things. First is the plan panel. You can see which tools the model decided to call. Second is the execution results. It's clear what evidence the final answer is based on. Here is a demo of the one-line mode. This is for automation or quick checks. We run a scripted query using the option ones. The key advantage is transparency. Even without the TOI, this mode prints what it's doing, so you can review the workflow before trusting the final answer. This also makes it easy to drop into shell scripts. It's fast, repeatable, and doesn't require an interactive UI. Now part 6, wrap up. For the contributions, Peixuan Li, which is me, in charge of the database and the planner architect. Zhengyang Li is the executor and infrastructure lead. Yanchi Wang is a front-end and integration specialist. For our lesson learned, the streaming parsing can be fragile. The database initialization can have risk conditions, and keeping a modular separation between the agent and the tools is really important for extending the system. Next steps are all realistic. We need to tighten the tool sandboxing, harden the streaming parser, and enrich the verification logic. Overall, this project is a valuable Rust educational example. It touches a synchronization system work, terminal UI, database persistence, and also an MCP-style method for exposing tools. Thanks for watching.